Assalamualaikum warahmatullahi wabarakatuh. I'm Alifia Matsani from Group 5. On this occasion, I will explain about the construction problem of Antiquity. Before that, I will introduce who is Hippocrates. Hippocrates of Chios was a mathematician who dominated the second half of the 5th century BC. He is known as the most prominent medical figure of all time, or father of medicine. Like Thales, he began his life as a merchant and ended up as a teacher. But he was less intelligent than Thales. Why? He had the bad luck that his money was robbed. Then he went to Athens to sue the offenders. When he was in Athens, he encountered three problems. The first is the quadrature of the circle. The achievements on which Hippocrates' fame were best related to the first problem. This problem sometimes called squaring of the circle. The question arises: it is possible to make a square whose area is the same as the area of the circle? According to tradition, Plato insisted that the task be done with straight and compass only, but that was not resolved despite the great efforts of Greek geologists and others. Their efforts proved fruitless in the 19th century. When mathematicians were finally able to prove that it was impossible to square a circle with just straight and a compass. Squaring a circle is the same as making a line whose length is the root of pi times the radius of the circle. This problem involves the formation of the transcendental number in the root of pi, whereas only certain algebraic numbers can be created with straight and compass. Hippocrates' attempts to square the circle led him to discover that there are certain areas of the plane with parallel boundaries. He showed that two hills could be drawn whose area is the same as the area of a right triangle. Starting with the right triangle ABC, it builds a semicircle on all three sides as shown. Hippocrates apparently knew that the areas of the circle were proportional to the squares of the lengths of their diameters. Thus, the area of the semicircle AB is proportional to the area of the semicircle AC. Is equal to AB square over AC square. This ratio must equals 2 for the Pythagorean theorem as applied to triangle ABC allows AB square equals AC square plus BC square equals 2AC square. Therefore, the semicircle AB has twice the semicircle AC. From this, Hippocrates concluded that the sum of the area of a small half circle is equal to the area of a large semicircle. The next step was to subtract the areas 3 and 4 common to both. The figure shows that the areas remaining, namely, the sum of the areas 1 and 2 of the two lawns and the area of triangle ABC are equal. But triangle ABC has area a half of AC times BC equals a half of AC square. so that the area of lune 1 plus the area of lune 2 equals a half of AC square. To put it another way, lune 1 has an area equivalent to half that of triangle ABC. The area of lune 1 equals a half of a half AC square equals the square of AC over 2. And the square of the lune has been found. The work of Hippocrates' paid lunes has been preserved through the writing of the 16th century commentator Simplicius. According to Simplicius, Hippocrates believed that he managed to get the square of the circle by the arguments he has described. He doesn't need to say, break the squaring of the circle. The fault lies in the assumption that each lune can be square. But this has proved possible only in the special case of concern to Hippocrates himself. The second problem is the duplication of the cube. In other words, finding a cube type that has twice the volume of the cube given. The formation legend of this suspicion is from the story of the Apollo altar, which should be twice as size then, and the story of a king who wanted to establish a tomb for his son. The first real progress in solving duplication problems made by Hippocrates. He shows that it can be reduced to find between certain lines and other lines twice as long as. In the current notation, if A and 2A are two given lines and X and Y are proportional, means that can be inserted between them. Then the lengths A, X, Y, and 2A are in geometric progression, that is, as stated. The first two ratios is A over X equals X over Y, then X squared equals AY. And the second ratio pair is X over Y equals Y over 2A, then Y squared equals 2AX. The equations were combined, then it will get X cubic equals 2A cubic. In other words, the cube that has hx will have double the volume of a given cube of HA. The third problem is the trisection of an angle, which is dividing the angle into three equal parts. Even though Hippocrates developed two of the three famous construction problems, he didn't make progress by making triangles. During the 2000 years of mathematical experts try in vain to divide three random angles. In 1837, Pierre Wonzel from École Polytechnique in Paris provided the first strong evidence about the impossibility to cut certain angles with straight and compass only. If the limitation imposed by Greek are relieved, there are various ways to divide the angle into the same three parts. The simple solution of this problem is to let yourself freely mark the parallel. The technique of playing parallelism until certain conditions fulfilled has been made by Archimedes. Let P or Q into an angle to be cut. See the picture. First, observe that by its construction, CD equals OC equals R, so the triangle ODC is isosceles. Hence, the angle of COD equals the angle of ODC. Because an exterior angle in a triangle is equal to the sum of the non-adjacent interior angles, it follows that in triangle COD, that is as stated. Also, in the isosceles triangle OCB, we have the angle of OCB equals the angle of OBC. Another appeal to the exterior angle theorem leads to the equality as stated. These various observations can be brought together to given as follows. Maybe it's just what I can explain. Thank you for watching this video, and wassalamualaikum warahmatullahi wabarakatuh.